Welcome to The Explainer. I am absolutely thrilled you're tuning in today because we're about to explore something that, honestly, it sounds like pure science fiction, but it's actually unfolding right now in research labs and enterprise servers all over the globe. We're going to be looking at how artificial intelligence is radically evolving to survive a very real, very imminent threat. And that threat? It's the end of human-generated data. Okay, let's dive right into this. 2026. Researchers are projecting that by this rapidly approaching year, we are going to hit a towering, immovable data wall. So what does this actually mean? Well, the high-quality, human-generated data we've been feeding into large language models to make them so incredibly smart, it's going to be completely exhausted. We are quite literally running out of human words, behaviors, and actions to teach our machines.
To navigate all this, we've put together a sort of step-by-step survival guide for the future of intelligence. We'll start by defining this looming data wall. Then, we'll look at the rise of digital twins, how these virtual worlds actually age, scaling with synthetic data, the differential privacy shield, and finally, a post-data intelligence era.
All right, Section 1, the looming data wall, exhaustion and paradox. And let me tell you, the stakes of this global data crisis absolutely could not be higher.
So here's the reality of the 2026 data crisis. We need massive, truly massive amounts of data for next-generation AI to keep learning. But since the easily accessible public data is mostly depleted, we're facing a massive ethical paradox. Do we just start scraping highly private, sensitive user records to feed the machine? We can't just strip out names and call it a day anymore. Traditional anonymization is completely failing against modern de-identification attacks. Sophisticated pattern matching can now reverse engineer basically any simply masked data to find out exactly who you are. So we need a massive, ground-up innovation to fix this.
Which brings us perfectly to Section 2, Rise of Digital Twins, Generating Realities. If we can't safely use real human data, well, we have to create a clone. We need high-fidelity mathematical mirrors.
To actually build these clones, we use a digital twin reference architecture. At the base, you've got the physical space, the real-world system with all its sensors pulling in data. Through a network, that physical space is continuously synchronized with the virtual space up top. Now, this isn't just some basic 3D model, right? It's a dynamic software system that actively mirrors the physical world, running predictive behavior modeling to tell us exactly what that real-world object is going to do next. It's like a crystal ball made of math.
Now, to make this work without smashing into that data wall, researchers introduced a fascinating, though honestly terribly named, framework called DDD-GenDT. It stands for Dynamic Data-Driven Generative Digital Twin. Really rolls off the tongue, right? But the absolute crucial takeaway here is zero-shot predictive inference. Look, in data-scarce environments, like highly complex Industry 4.0 manufacturing floors, collecting thousands of data points to train a model is just way too expensive. This framework uses generative AI and large language models to clone a system and predict its future behavior using literally zero task-specific training data. Zero. It just looks at a super short window of current operations and it predicts the rest.
Let's move to Section 3, Aging in Virtual Worlds, the NASA case study. We're going to zoom into a specific micro-level example here to really make this tangible.
But before we look at the data, we really need to understand a concept called DT aging. And why this matters is absolutely profound. You see, smart infrastructure won't just learn a task once and then stay static forever. Two identical machines are going to experience totally different workloads and unique environmental stressors. So DT aging means the digital twin autonomously grows old. It adapts right alongside its physical counterpart, reflecting all that cumulative wear and material degradation over time. Now, what's really interesting is seeing how this actually looks in practice. We can compare physical data from a NASA CNC machining spindle motor directly with a dynamic prediction output from GPT-4. As the physical cutting tool wears down over multiple runs, the current it draws changes. It gets super complex and nonlinear. But here's the wild part. The framework extracted just a tiny observation window of the motor's current, fed it into the LLM as a simple sequence of numbers, and GPT-4 accurately predicted the tool's nonlinear wear dynamics for the next run. And remember, it did all this with zero prior training data on this specific machine. None. Just think about that margin of error for a second. It is absolutely staggering. The GPT-4-based digital twin achieved an average error of just 0.479 amps out of a maximum 10 amp spindle current. That proves beyond a shadow of a doubt that we can use generative AI to basically perfectly predict mechanical breakdowns in complex physics before they ever happen in the real world. It's a true game changer.
Okay, so Section 4, Scaling with synthetic data, the virtual sandbox. Because if we can clone a single machine that accurately, what happens when we zoom back out to the macro level, right? We take those exact same generative principles and scale them way up, using models like generative adversarial networks, or GANs, and variational autoencoders. Look, we aren't just creating simple mock data with fake names here. We are building massive mathematical mirrors of entire populations. These models learn the underlying probability distributions of highly sensitive real-world data and synthesize completely new records. They capture the true nuances of human behavior, including all those vital little edge cases that usually just disappear in standard statistical sampling.
And there's an incredible secondary benefit to this whole process: neutralizing bias. Since we're essentially generating the reality, we can control it. Synthetic records are actively being used right now to intentionally oversample underrepresented groups, which corrects historical imbalances in the training data. By doing really rigorous algorithmic auditing, developers are successfully applying this to create much more equitable AI models for incredibly sensitive applications, things like healthcare diagnostics and financial credit scoring.
Moving on to Section 5, the differential privacy shield, protecting the clones. This brings us to a very natural follow-up question. If we're using highly sensitive data to train these AI models to generate high-fidelity clones, how do we guarantee that the AI hasn't memorized private things and isn't just going to leak them? Well, the answer is differential privacy. Think of this as a shimmering mathematical force field. It provides mathematically provable privacy guarantees by injecting carefully calibrated randomness or noise into the data analysis. This force field ensures that even if a super sophisticated attacker tries to reverse engineer the AI or the synthetic data, it is statistically impossible for them to determine if any specific individual's data was ever included in that original dataset.
So the crucial point here is balancing what researchers call the privacy utility trade-off, specifically looking at the privacy budget, represented by the Greek letter epsilon. A lower epsilon means stronger privacy, but you add way more noise, which means less accuracy. A higher epsilon gives you less noise and more accuracy, but obviously weaker privacy. It's kind of like adding audio static to a radio broadcast. If you calibrate it just perfectly, you can still hear the song clearly, so you get the aggregate analytical value, but the static prevents you from identifying the specific singer's voice. You protect the individual while keeping the broader insight.
Now, there are a few ways to apply this static, and we'll fire off these common mechanisms pretty quickly. You've got the Laplace mechanism, which adds numerical noise, the Gaussian mechanism for more complex queries, the exponential mechanism for non-numerical stuff, and DDD-GenDT, which applies this privacy directly during machine learning training. Actually, organizations like the US Census Bureau and Apple use these exact mathematical tools on your data today. It allows them to safely extract massive, valuable aggregate insights without ever risking your individual re-identification. All right, Section 6, a post-data intelligence era, the 2027 shift. Let's bring the crisis, the clone, and the shield all together into a single roadmap for the future. Let's move to this roadmap and see how this all builds. We already know 2026 is the data wall. Presently, we're seeing the rise of decentralized training, where differential privacy lets competitors collaborate and train AI without ever sharing proprietary user data. But the massive shift? That happens in 2027. Experts predict that by 2027, 90% of enterprise AI training will migrate away from raw human data entirely. The vast majority of our machine intelligence is going to rely on these private, synthetic sandboxes. You see, adopting these ethical, privacy-preserving architectures isn't just some clever technical workaround. It's absolutely crucial. It's literally the only way to scale intelligence without completely losing public trust. But I want to leave you with this final, provocative thought. If AI no longer needs our data to learn, what will it discover in the synthetic realities of its own making? When machines learn from digital twins that perfectly mirror physics and synthetic populations that perfectly mirror society, the ceiling for discovery is absolutely limitless. Thank you so much for joining me on this deep dive into the future today. Keep questioning, keep learning, and I'll catch you on the next explainer.